How do projectile motions work? So to start and to understand how projectile motions actually work, first we need to talk about kinematics, which is the study of motion without considering the physical properties of the object that is in motion. So this is about how things move and less about why they move. So just think about, which direction a thing is moving or how far or fast it's moving, and not why it's going so fast or why it's going so far. These kinematics that I'm talking about are made up of vectors, angles, acceleration, time, the final velocity, and the initial velocity, and of course the distance. Kinematics is used to measure any of those three, or sorry, not those three, but any of the things that I listed, acceleration, time, final velocity, initial velocity, and distance, by using a certain set of equations. You can see here you have a set of 5 equations, all of them solving for different things. We actually have 2 for final velocity. We have final velocity is equal to velocity initial plus AT, which is acceleration times time. That little triangle you see in A is equal to triangle V divided by T. That's going to be the change in velocity, so it's the change in velocity, so that would be final velocity subtract initial velocity, and you divide that by time to get your acceleration. Distance you see a lot, especially for horizontal projectile motion. We use that a lot in our math. That is d is equal to VIT, which is velocity initial times time, plus 1/2 of AT squared. So yeah, that's what that t divided by t is. That's AT squared. So yeah, those are the main equations that we would use.
Vectors are lines that represent magnitude and direction on a graph. In a projectile motion, there are 2 vectors, one on the x-axis and one on the y-axis. These 2 vectors are in different directions on a scale, so that means that they are independent to one another. This picture right here is an example of a vector. Free fall. Free fall is when an object that is in the air is only affected by the acceleration due to gravity. Gravity on Earth is negative 9.81 meters per second squared. Objects in the free fall accelerate at a constant rate in the y-axis. Horizontal speed is not affected while in a free fall. Horizontal projectiles. Horizontal projectiles are a combination of kinematics, vectors, and the idea of free fall. Horizontal projectiles have an initial velocity that is created by a certain force. Once the projectile is launched, it is in free fall. Instead of only being in the y-axis, though, it also has a vector in the x-axis. This means that while the projectile is free falling in the y-axis, it also has a constant velocity in the x-axis. The purpose of this lab was to determine if the path of the projectile could be predicted with the math, and if the rings could be placed at different points in the projectile's path so that it would go through them. We believe that if we used the right mathematics, then the metal ball would launch and go through all 5 of the rings.
So next we have the methods. This method section is going to teach someone who does not know what is going on in this particular lab how to replicate the lab without using I statements, we statements, things of such, so we only talk in the third person. And you'll see that as I read this out loud to you. So here it is. The materials needed for this experiment are a vernier projectile launcher, a small metal ball, rings, poles, clamps, slow motion capable cameras, and meter sticks or multiple meter sticks. You'd probably want multiple meter sticks, as you'll see later on as why too. I suggest multiple, but first we use the projectile launcher. It has to be fired straight up at a 90-degree angle with meter sticks stacked on top of each other. We did it so it's 1 meter, 2 meters, 3 meters. And that we do that to determine the max height that the launcher will reach at a certain PSI. To get the distance, we can use, or we just visually see the distance, how the max height. We then plug in the distance, and we can physically see the time as well, or we could calculate for time if we wanted to using one of the previous equations in the kinematics section I also talked about. But we use the equation V is equal to d divided by t, and that would give us our initial velocity. And that would be after it leaves the projectile launcher. The formula, the V times cosine of theta, which is our angle, which would be 45 degrees, as that what we were tasked to is to shoot the ball at a 45-degree angle. and that can be used to find the velocity in the x direction, and we can use velocity times sine of theta, our angle, which is 45, to find the velocity in the y direction. Next, we have to position the projectile launcher, and we have to find that exact position. Then we need to show calculations in order to determine where to place the rings relative to the launcher. So if we have a launcher here, we need to do calculations. We first need to determine a distance that we want, and they all cannot be equal distant to each other. So you determine a distance you want, and you set it to that distance, so like 1.6 meters, 0.3 meters. These are all just random distances that are just coming out of my mind. You'll see which distances we choose later on in the video, but yeah, just for the sake of things right now, just think of random distances, and that's how you would do it. Next, the poles are placed next to the distances found, and that's talking about the height of the poles and where the rings need to be. And we use the meter sticks to measure the exact position. Although you see later on in our trials that we didn't do that so well, our math was correct. And we need to pump. The projectile launcher, how it works is it's pumped, and then the PSI that is generated from that air pump is then used to shoot the metal ball out of it. So we have to pump, and we get slow motion cameras positioned at different angles. What we did one at the start, one at the end, one at the middle. You'll see the videos from the middle. And finally, we launch the ball while recording it, and we review the footage to see if the ball actually went through. And we get 3 trials. We did not get the prizes, which was get a lab free card, bonus points, and a physics toy. I'm so sad about that physics toy. I really am. But all 3 of our trials did not go as planned. So after each trial, it is recommended to make adjustments. So we made adjustments, and it maybe just didn't work out for us. Hopefully it will for you.
Okay, so the first thing we need to figure out was the maximum height of the launcher. So what we did is we had 3 meters of meter sticks, and we launched the ball at a 90-degree angle to see the maximum height of the ball. And as you can see in this video, it averaged around 2.51 meters, which I will show. While this one was around 2.48, we did multiple tests and we got around 2.51 meters.
So for each trial, we had to take a video in slow-mo to see our results. So I will show you the first trial now. As you can see, the ball comes up here and it hits the 3rd ring. So the reason that happened is the 3rd ring, we had our placements off, it was a little bit too far out. So if it wasn't, it maybe gone through, but never know. After our first trial, which had failed, we had to make some adjustments. So we ended up moving our 3rd ring over a little bit, and I'll play the trial now and show you what went wrong. So you come out here, that's the first, second, third, it misses the 4th, it misses the 5th. So we believe that our 4th ring was a bit too high, and that our 5th ring was a little bit too far out, so we have to make adjustments again for the 3rd trial.
So after our first 2 trials, both mistakes, we knew we needed to make some changes to our rings. And so after that, we still managed to fail. While I got through the first 3 and the 4th one, it still managed to hit the 5th one. And that's not because of the math, but that's because of the bad placement of the rings. And as you can see here, goes to the 1st, 2nd, goes to the 3rd, goes right through the 4th, and it hits the bottom of the 5th. So while the mathematics did work, there is a lot of uncertainty with human error of placing the rings. I also have Logan Goodrich with the analysis of this video.
All right, so if we wanted to calculate the velocity that Kyle Whiffen was running away from Carter Scheimer here in the background, we could clearly do so. If I could just come over here and highlight for you what happens here. If you could just give me 1 second, I'm just gonna circle this really quick for you, and then we're gonna go back here. Pause this here. If you look right here, right in this area, you're gonna see this guy. Now, this is Carter. He's chasing after Kyle Whiffen for unknown reasons. This is Kyle Whiffen right here. Yeah, it's Kyle. So if we wanted to, we could get his velocity, and we could probably measure the distance from right here, this line, to this line over here, which is kind of hidden. So yeah, if we wanted to do that, we could. Also, you also notice Luke over here, his very shocked expression after the fact, as he was very upset that we didn't get it, and we didn't get any bonus.
So
It's sad.
we learned a lot from this. We not only learned from two-dimensional kinematics, but we also learned from velocity and acceleration from Kyle and Carter in the background. So there's a lot of kinematics in real world places, just as ran by him in the hallway. So the first thing that we did is we needed to find out the maximum velocity, the average velocity of the ball when it hits maximum height. So the maximum height was 251.4 centimeters, which equated to 2.514 meters. And we used the velocity equals square root of 2AD. And we plugged it in and we got 7.02 meters per second for the velocity. Alright, so the next thing that we had to do was we needed to find the velocity for the x and y axis. So for the x-axis, you use the measurement of the velocity times cosine of the angle. And the angle was 45 degrees. And for the y, we used the measurement of the velocity times the sine of 45 degrees. And it turned out to be 4.96 meters per second for both x and y axis.
So next thing we need to figure out is the half time of flight, or half the time it took after launch for the object to reach the ground. To figure that out, we do t is equal to change of velocity over a, and the change of velocity is the final velocity minus the initial velocity. So that would be 0 meters per second minus 4.96 meters per second, and you divide that by the acceleration due to gravity, which is negative 9.8 meters per second squared. When you do that, you get 0.5 seconds.
Go. Next, we need to find the distance that it traveled at halftime in both the x and the y direction. So to find it in the y direction, we use the equation d equals vit plus 1/2 at squared. And we plugged in these numbers over here to get 1.25 meters. And to get the distance in the x direction at halftime, we used d equals vt and used these numbers over here to get 2.5 meters.
So our objective was to get a ball launched from a certain point at a certain velocity to pass through each of these 5 rings that we had to set up. The first ring, we made up our own distances. They all had to be unequal to each of each other. So this couldn't be equal to this one, or this one, or that one, or that one. So we chose 0.9 away from the launch point for the first one. And we plugged that distance into this equation with the velocity initial to get the height of the ring, but we also had to calculate for an error in which the ball is elevated 0.148 meters off the ground, or 14.8 centimeters, so we had to add that on after we put it out. So after the addition of 0.148 meters, we get 0.88 meters, and that's how tall the first ring has to be. We do the same for the second and the third, and after the addition of 0.148 meters, we got 1.24 meters high for the second ring, and 1.39 meters as the third ring, which was the middle ring. To calculate the fourth and fifth ring is slightly different. The velocity initial is not 4.98, it is 0 because we started from the middle, since we calculated for half time, not the whole time. So we have to take that into account. And after that, and the addition of 0.148 meters, 1.2 meters for the fourth ring, and 0.79 meters for the fifth ring. After we set out our distance of x with 0.9, 1.6 meters, 2.5 meters, 1 meter, and 1.75 meters, we have to calculate the time it takes from the ball at the starting position to pass through each ring. To start out, we use the equation t is equal to d divided by average velocity. Our average velocity is 4.98 meters per second. So if you plug in this distance with an average velocity of 4.98 meters per second for each of these equations, you'll get 0.18 seconds for the first ring, 0.32 seconds for the second ring, 0.51 seconds for the third ring, 0.20 seconds for the fourth ring, and 0.353 seconds for the fifth ring. You'll notice that these are smaller than some of these. That is because we calculated for half time of flight. So if we do that, then this is actually the time it took if you start from the middle ring. So if it took 0.51 seconds to get from the starting position to the third ring, then it took 0.2 seconds to get from the third ring to the fourth ring, and 0.353 seconds to get from the third ring to the fifth ring.
The purpose of this lab was to see if mathematics can be used to determine the path of a projectile, not including resistance or any other force except the force to launch the projectile. Our mathematics did work for assuming the path of a projectile, although there is much uncertainty in the measurements such as the height and distance of the metal rings being set up properly, the angle of the metal rings, and the difference in pressure in the launcher.
Go.
Okay, so the next thing that we needed to find out was the time to get to the middle.
Go.
So the next thing we needed to figure out was half the time it took to hit the ground. So the next thing we needed to figure out was the time it. Oh my god.
Go.
So the next thing we need to find out was the time it takes to. All right.
We have to calculate the time it takes for the ball to pass from the start of the ring, or sorry, the start.